Hi, everybody. Thank you for watching this recording. I'm very happy for the opportunity to share some of my math with you all. Thank you to the organizers of Café con Leche for this lovely opportunity. So today I'll be telling you all about generalized parking function polytopes. And I'll begin by saying who I am. My name is Andres Vindas Melendez, and I'm a NSF postdoctoral fellow and lecturer at UC Berkeley. And in a few months, in July 2024, I'll be joining Harvey Mudd College as a tenure track assistant professor. So my work is in geometric combinatorics, which is combining combinatorial tools to study things in discrete geometry. And so before I tell you about the objects that we're going to study, I want to acknowledge my two collaborators on the project that I'll tell you in a bit. And so on the left, we have Mitsuki Hanada, who is a third-year PhD candidate at UC Berkeley. And on the right is John Letfer, who's also a PhD candidate, third year at UC Berkeley. And so we've had a lovely time working on this project. So first, let me tell you about classical parking functions. So this is how Conham and Weiss in 1966 have described or written about classical parking functions. So this is the parking problem, the case of capricious wives. So let ST be a street with P parking places. A car occupied by a man and his dozing wife enters the street at the left and moves towards the right. The wife awakens at a capricious moment and orders her husband to park immediately. He dutifully parks at this present location. If it is empty, it parks, and if it's not, it continues to the right and parks at the next available space. If no space is available, he leaves the street. So this is the setting that we're going to work in. But before we get to the mathematics, I want to note that mathematics is done by people, and the way people write about it, I would not myself write about such a scenario in this language. And so we should be mindful of how we write. But that is a discussion we can have when we chat all together. So let me tell you a slightly modified way of rephrasing this parking scenario. So I'm going to say I have n cars and a one-way street. So here are our n cars, and here's our one-way street with n parking spots. Each of the car, let's say car C sub I, has parking preference A sub I. So if A sub I is occupied, then C sub I takes the next available parking spot. We call A1 through AN a parking function of length n if all the cars can park successfully. So let's see an example. Let's say that we have n equals to 2. So we only have 2 cars. So what are the options for these parking preferences? Well, if car 1 has preference 1, it comes into the street. Of course, it's the first car, so no cars have parked, so it gets to park in parking spot 1. Let's say car 2 also has parking preference 1, comes in, sees that it's occupied, but it's able to park in parking spot 2. So that's good. So 1, 1 is a parking function. Similarly, 1, 2 is a parking function, and 2, 1 is a parking function. But note that 2, 2 is not a parking function. So let's see why that's not the case. Car 1 has parking preference 2, so it comes in, goes to parking spot 2, sees that it's empty because it's the first car, and it parks. And car 2 also has parking preference 2, comes in, and sees that car 1 is parked in parking spot 2, but there should only be 2 available parking spots from which C2 can park in, because n is equal to 2. And so it sees that the second spot is occupied, but again, this is a one-way street, so it has to leave the parking lot. Maybe here's a good opportunity for you to pause the recording and try to figure out how many parking functions are there for n equals 3? Maybe you didn't want to pause, but if you did, you might have figured out that there were 16 of them. And here they are listed. Okay. So continuing with the setting of classical parking functions, we're going to let alpha be a list a1 through an of positive integers. And we're going to take their non-decreasing rearrangement. So we're going to take b1 is less than or equal to b2 is less than or equal to b3, and so on, to be the non-decreasing rearrangement of alpha. Then this proposition says that alpha is a parking function if and only if b sub I is less than or equal to I. That means if we look at the non-decreasing rearrangement, the number has to be less than or equal to its index, or its position in the list. Okay. As a corollary, we have that every permutation of the entries of a parking function is also a parking function. And so enumerating the parking functions of length n has a very nice formula. This is given by Pike and Conham and Weiss. And the formula is n plus 1 to the n minus 1. And I should note that Conham and Weiss were studying parking functions for to study hashing problems motivated by computer science. So how do I think about geometric combinatorics, or what is an approach that I take to doing geometric combinatorics? So we take our favorite combinatorial object, and if we can associate some sort of list, I want to take my combinatorial object and find the underlying polytope. Okay. And so in this setting, the combinatorial object is the classical parking function. So before I define a classical parking function, let me just quickly define a polytope. So a polytope can be thought of as a higher dimensional generalization of a polygon. So in 2 dimensions, we have polygons. In 3 dimensions, we have polyhedra. And so on. In higher dimensions, we can say it's a n-dimensional polytope. And so 2 equivalent definitions of polytopes is that the first one is that it's the convex hull of finitely many points. The second definition is that it is the bounded intersection of finitely many half spaces. So if you have a system of linear inequalities and the solution set is bounded, then that creates a polytope. And so what we're going to do now is take the list of parking functions of length n, treat them as points in n space, and then we're going to take their convex hull. So I like to think about the convex hull as throwing points into space and then saran wrapping them as tight as you can. And so what you're doing is you're getting a shape with flat sides, okay? And so here are the parking functions for n equals 2, 3, and 4. So we saw earlier that n is equal to 2. For n equals to 2, we have 3 parking functions. And if we plot them as points in in R2, we should get this triangle. Similarly, this is the shape that we get for PF3. And here is a 4-dimensional parking function polytope projected into 3 space. And so this is a representation. We call it a Schlegel diagram. Okay. Note that not all the parking functions are vertices of our polytope. Okay. So a subset of the parking functions will be vertices. So in 2020, Richard Stanley asked for the number of vertices of the parking function polytope, the number of faces, the number of lattice points, and the volume of the parking function polytope. Okay. these were resolved by Amanbayeva and Wang in 2022. And so what we want to do is do a generalization of this parking function polytope. So we're going to take a vector x to be this x1 through xn of non-negative integers. So we define an x parking function, so this is a generalization of a parking function, to be a sequence a1 through an of positive integers. Similarly to the classical setting, we're going to take its non-decreasing rearrangement, b1 is less than or equal to b2, is less than or equal to b3, and so on. But in this case, the x parking function has to satisfy b sub I is less than or equal to the partial sum x1 plus x2 up to xi. Okay. And enumeratively, this is a challenging problem to enumerate all the x parking functions for general x. So in 2001, Catherine Yan, which also can be accredited to Pitman and Stanley, say that for x, in the special case where we have a first entry A, and then the rest of the entries B, 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 so all the same entries, the number of x parking functions for that particular x is given by A times A plus NB to the n minus 1. So we can see if through an example that this generalizes the classical setting when we take x to be 1, 1, 1, 1, 1, right? Because we would have 1 times 1 plus n times 1, which is n plus 1, to the n minus 1, which is this. So we recover the same formula we saw earlier for the number of classical parking functions. So following the same idea from Yan of using x equals to ABBBB, that's the setting that we're going to be working with. Right? So we define the x parking function polytope for specifically for x equals to ABBBB, and we denote it x sub n of a comma b. We take this to be the convex whole of all x parking functions of length n in Rn for that particular x. Now we can think about this for general x, but again, I emphasize that because of the difficulty in enumerating those parking functions, we restricted ourselves to this particular setting. So here are the x parking functions polytopes, so again, for x of some specific a and b, okay, for x equals to 3, for n equals to 3, correct. So one thing to note is that when we have a, so this first entry in our x vector, to be greater than 1, there are new facets that do not appear when a is equal to 1. So here, a is equal to 1. We see that these are combinatorially equivalent. But when a is greater than 1, in this case, a is equal to 2, we see that other facets appear. Okay? So again, we focus on x equals to a, b, 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 following the work of Yan. So in the same spirit as the questions that Stanley posed, originally we studied the phase structure of this x parking function polytope. So in our first proposition here, we are able to tell you the structure of the vertices of this polytope. And so they turn out to be all permutations of this form, where we have k many ones in the first entries, and then these n minus k entries have this particular form. And in particular, this allows us to write down formulas for the number of vertices. So again, we saw that things change when A is equal to 1 and when A is greater than 1. And so we have two slightly different formulas. So like I mentioned in the beginning, when thinking about polytopes, we think about the vertex description or the convex hull description, and then we can also think about the inequality description, right? That's the bounded set of these inequalities. And so here we present a list of inequalities that the X parking function polytope satisfies. In particular, these are, this is a minimal inequality description, meaning none of the inequalities are redundant. So as a corollary to the inequality description, we are able to enumerate the number of facets of this polytope, which is given by these two equations, these two formulas, when A is equal to 1 and A is greater than 1. And then we have this proposition that says for each vertex of the X parking function polytope, or XNAB is what I'll refer to it, there are exactly n edges of the XNAB with V as one of the vertices. So in other words, this is a simple polytope. Okay. And we're actually able to take it further than the than just the facets. So the facets are the n-1 dimensional faces, but we can tell you the number of any k-dimensional faces for this polytope. And this brings in some nice combinatorics dealing with the Stirling numbers of the second kind. And I might have slightly mentioned this earlier, but if we take a fixed n and a equals to 1, then no matter what b you choose, all these X parking function polytopes will be combinatorially equivalent. What I mean by that is that they will have all the same face structure. Okay. And now we want to think about volume. Okay, so volume for the classical for the X parking function polytope. So the first proposition says that if we take A equals to 1, then for any b greater than or equal to 1, it would just be a b dilate of the classical parking function polytope. Okay, remember, if we take our X vector to be 1, 1, 1, 1, 1, that's the classical parking function polytope. Now for a fixed A greater than or equal to 1, this particular X parking function polytope is a b dilate, meaning we're scaling the polytope by a value of our chosen value of b of XNAB, where A is any fixed integer greater than or equal to 1, and B is all 1. Okay. So we are able to give a recursive formula for the volume of this polytope. This is a generalization of the recursive formula that Amanbayeva and Wang give in their paper for the classical setting, for the classical parking polytope. But depending on your flavor of mathematics, you might not be satisfied with a recursive volume formula. So what we want is a closed form. And so that's what we give. We give the arguably the simplest closed form that is known for this polytope. And from this generalization, or from this closed formula, remember, we can obtain we obtain the classical parking function polytope when we take the X vector to be all 1s. So we can obtain a closed formula for the classical parking function polytope by setting A and B equals to 1. And so this is very, very nice for us. And this polytope also presents the opportunity to connect it with other well-known polytopes. So if we were to just look at the weakly increasing X parking function, the X parking functions, and again, we take their convex whole, then this this polytope is related to a polytope that has been well studied in the literature, known as the Pitman-Stanley polytope. And so the Pitman-Stanley polytope is defined here by these inequality description, And so the weakly increasing X parking function polytope is integrally equivalent to this specific Pitman-Stanley polytope. What I mean by integrally equivalent is that it's not only combinatorially equivalent, not only does it preserve the phase structure, but it preserves the number of lattice points. Okay? And because the Pitman-Stanley polytope is very well studied, we are able to obtain a corollary that tells us the number of lattice points in the teeth dilate of this weakly increasing X parking function polytope, which is given by this formula. Now there's another polytope that has been getting attention recently, which is known as the partial permutahedron. This is the polytope with all permutations of the vector 0, 0, 0 up to some value defined by this inequality, and then it satisfies these entries. Okay, and so those are its vertices, and so we're able to tell you that when these partial permutahedra are exactly X parking function polytopes. Okay, in particular, when we take the classical parking function polytope, this gives us a very nice partial permutahedra. So now let's revisit the classical parking function polytope. Okay. So we show that the classical parking function polytope is integrally equivalent to this partial permutahedron when we have this, when we take n, and then in the notation that we used for their partial permutahedron p, we take it to be n minus 1. So we have now the classical parking function polytope can be obtained by specializing our generalized parking function polytope, or this xnab polytope, when x is equal to 1, 1, 1, 1. And we show that that is integrally equivalent to this partial permutahedron, this specific partial permutahedron. Okay. So an additional result on the phase structure of the classical parking function polytope is that the regular permutahedron, so what is the permutahedron? If we take the vector 1 through n, and we take all permutations of that vector 1 through n, and take the convex whole, that is known as the regular permutahedron. Okay, so what this result says is that the regular permutahedron appears as a facet, so an n minus 1 dimensional face of the classical parking function polytope exactly once. And the second point of this proposition says that the n minus 1 dimensional parking function polytope, so the parking function polytope that's 1 dimension lower, appears as a facet of the n parking function polytope exactly n times. So let's see that through a picture. Here is the 2-dimensional parking function polytope on the left, and on the right is the 3-dimensional parking function polytope. So let's see, in orange, we will see the regular permutahedron of the corresponding n in orange appear only once. So there it is. For n equals to 2, the regular permutahedron is a line segment because it's the convex hull of the permutations 1, 2, and 2, 1. And then for the three-dimensional parking function polytope, we should see that the hexagonal facet is the regular permutahedron appearing once. This is the permutations of the vector 1, 2, 3. And how many are there? Well, it's 3 factorial, so it's 6, and these are the vertices, so we should get this hexagon. And then we see that the n-1 dimensional parking function polytope appears dimension many times. So for the 2-dimensional parking function polytope, we should see the 1-dimensional parking function polytope appear twice. So in this case, it's these 2 line segments. And so we should expect it 3 times in the other picture. And so here they are. All right. And so let's come back to this notion of volume for the classical parking function polytope. So one of our main contributions for this project is that we give equivalent formulas for the classical parking function polytope. And so the first one is the recursive formula. And this is, I should say, is worded for the normalized volume. What I mean by normalized volume is that I take the Euclidean volume and multiply it by dimension factorial so that I obtain an integer, because it's the case that Euclidean volume is not always integral. So a recursive formula is due to Amanbayeva and Wang. Behrend et al. Also give this other recursive formula by studying, in which we can obtain from studying partial permutahedra. By specializing our closed formula for the X parking function polytope, we are able to get a closed form for the classical parking function polytope. And then what's nice is that we are able to show 2 other formulas are equivalent. So this is another closed form. 4 and 5. 4 is another closed form. And this is due to Shevelev from the 90s, but Shevelev wasn't studying parking functions. Okay, and so what we do is we show that our formula 3 is equivalent through 4. And then Shevelev showed that 4 was equivalent to 5. And so this formula that's presented in 4 equals the number of n by n 0, 1 matrices with 2 1s in each row that has a positive permanent. So now that's a mouthful, but that gives us some interpretation for the volume of this classical parking function. So what's the proof idea? The first one is we show the equivalence of 1 and 2. This follows from the proposition that I mentioned earlier, that there is an integral equivalence between the classical parking function polytope and this specific partial permutahedron. Now we derive 3 by using the exponential generating function for the recursive formula in item 1, and then we use analytic combinatorics tools and analytic number theoretic tools, such as Ramanujan's master's theorem, which is, at least to me, very surprising, but very nice. I did not expect to use it for such a problem. And then we use the Lambert function, Charlier polynomials, and generalized Laguerre polynomials to simplify our results. And so this is the beauty of mathematics, where unexpected tools come into play. And so a lot of these tools are actually, these polynomials appear in the study of mechanical arithmetic and mechanical engineering. And then we show that item 3 and 4 are equivalent by using Zeilberger's telescoping algorithm. And then item 4 and 5 are shown to be equivalent by Shevelev. And so one open problem is to find a combinatorial proof for item 5. That is still open. And now I want to just show you a picture of some other collaborators. So with this amazing group of graduate students and faculty, we are continuing to study these parking function polytopes, specifically the X parking function polytopes for general X. And so we have some nice results coming out of this that I hope that I can share with you all sometime soon. So with that, I will thank you. Gracias. And if you're interested in our paper, it's on the archive, and you can find it under the title Generalized Parking Function Polytopes. All right, I look forward to talking with you all in a little bit.